All right, so hello everybody. My name is Daniel Piacitelli. I'm a grad student at Rutgers University working with Allison Brooks, and I'll be presenting my work on surveying the CGM around simulated dwarf galaxies. And so, like it was mentioned, there's been a number of talks that have already kind of set up dwarf galaxies and why we care about their CGM. So I'm going to kind of move quickly past that. But first, I do want to just quickly define, we treat dwarf galaxies as anything below a virial mass of 10 to the 11. So that's roughly about 10% the virial mass of the Milky Way. And as has been kind of explained previously, because of these lower masses and the shallower potential wells, dwarf galaxies are much more sensitive to supernova feedback. And this heavily shapes their chemical evolution and results in lower metal retention rates. However, in simulations, these outflows that are really shaping this or causing this are not strongly in agreement with observations. So what this kind of leaves us with is that the CGM around dwarf galaxies is not only going to be a key component in understanding the evolution of dwarf galaxies, but could also be a powerful tool in informing and constraining our subgrid physics in our simulations. So observationally, there's been a number of papers that have looked at the CGM around dwarf galaxies. I'm focusing on low redshift, and so specifically this work done by Yang Zhang in 2024, which focused on isolated low redshift or local dwarf galaxies. And so not only did they contribute their own sightlines, but they also compiled a lot of the existing observations, summarized in the bottom of the plot that you can kind of see. And so what they found, this is a column density profile of H1 with respect to normalized impact parameter for their full sample. And so each data point is an observation. It is a solid marker if it is a detection, an open marker for a non-detection or an upper limit, or a solid marker and an upward-facing arrow for a saturation. And then each marker is color-coded based off of the stellar mass of the dwarf galaxy it is around, and a different marker style for which paper it came from. So a lot of different axes. But generally what we see with H1 is that we have detections. We have a common H1 detection around dwarf galaxies. So there is some material out there. And generally you can see a declining profile. If we move into low ions and metals, this is not exactly the same. We do see roughly, very vaguely, if you squint your eyes, a declining profile. But really what we see is a lot of non-detections in the outer CGM, and all of our detections are within half a virial radius. And I'll also point out that this is despite some very high signal-to-noise spectra. So most likely whatever material is out there in these ions is well below detectable limits. And then if we move into slightly higher ions, we see a similar picture as well. You can see carbon-4 is slightly passing out past half a virial radius, but still a lot of non-detections in the outer CGM. And then in addition to what is shown here and not covered in this work is there have been oxygen-6 detections, like was covered previously. And so what that really implies is that there is going to be most likely a warmer component in the CGM around dwarf galaxies that these ions are not probing. Now for the rest of my talk, I'll introduce the simulations that I'm using, then I'll compare our column densities in our observations, or in our simulations to observations, and then I'll give a brief temperature census, and because I kind of blew through my introduction, I'm going to try and squeeze in a fraction of metals retained in the CGM as well. So for my work, I use two different suites of simulations, the Marvelous Dwarfs and the Marvelous Marian simulations. These are both cosmological zoom simulations run with smooth particle hydrodynamic code, Changa. And I've highlighted the force resolution and gas mass particle resolution, which are slightly different between simulations. And they do differ in supernova feedback models as well. And so what this really means is that they make different decisions about how to model the evolution of the supernova, but they still impart the same energy and mass into their surrounding, gas. And so with these simulations, we select galaxies that are within the stellar mass range of the observed sample and isolated at z equals 0. And here's a stellar mass histogram comparing the observed sample to our sample, the M&M sample. That took me a while to figure out for a name. Yeah, so we see some exciting agreement, and we also see we find about 64 galaxies individual galaxies that we can compare against. And I'll just highlight that despite the differences in resolution and feedback modeling, we see no differences in their CGMs. So we do feel confident we can compare these or combine these two simulations as one sample. This is also coming from previous work that has specifically looked at how our simulations change when we move from blast wave to superbubble. And in terms of stellar mass to halo mass relation, mass metallicity, and size to mass relation, we see no distinct difference. And so we feel very confident we can use this as one sample to study the CGM as well. And so with these simulations, we then draw synthetic sightlines around all of our galaxies and derive synthetic column densities in a variety of ions. Here what I've shown is the same adapted figure from Yang Zhang's paper from before with the observational points, and then underlaid is the histogram of column densities bin by stellar mass. And so on the far left-hand side is our highest mass or highest stellar mass bin, and all of the column density values for those. And then as we move to the right of the slide, we decrease in stellar mass. And so what we can see is that not only do we see some agreement with the existing observations we have access to, but we also see a steep inner H1 profile that about at half a VO radius flattens out. And as we move down in stellar mass, that steepness kind of shallows out. Now, if we move into low ions like silicon-3, which I've picked out silicon-3 because it has the most detections, but it's a similar picture for all the other low ions as well, we see that these low ions have really steep profiles. And because of this, they plummet so quickly that they're below detectable limits by half a VO radius, in agreement with all these non-detections we have in the outer CGM as well. Now for carbon-4, or slightly higher ions, this is a slightly different picture. The profile is a little bit flatter, which makes sense because it's a slightly higher ion. But what that also means is that it's not entirely below detectable limits at half a VO radius. In agreement, again, with these observations that are starting to kind of push us past into the outer CGM. And so I think that's really exciting that in addition to oxygen-6, carbon-4 is also going to be really useful in both probing different phases of the CGM, but also slightly further out. Now, the next question that we can also ask is these lower ions that should be existing in cooler gas, how does that kind of make up the CGM in terms of percentages? And so here I have, for each of our galaxies in the M&M sample, I've counted up the total mass in the particles within that are around 10 to the 4 Kelvin. And so this is the cool phase of the CGM. And I've plotted that against each galaxy's stellar mass. And then the one data point we have is the empirical model prediction provided by Yang Zhang's paper as well. And so generally what we see is that the mass in the cold phase decreases with stellar mass as well. And we do see some agreement with Yang Zhang's paper, this one data point. So not a huge data sample to compare against, but there is some more empirical models that we're looking into that we can compare against as well. Now, the other question then is, this is just one phase of the CGM. So what about the warmer phase? And if we do the same analysis with the slightly warmer phase, we see that this dominates the CGM mass. And so not only is the, across stellar mass, the warm CGM does constitute the majority of the baryonic fraction, as well as like total mass in the CGM as well. So I think this really motivates that beyond these lower ions, it will be really interesting and important to detect this warmer phase and study it to really understand the CGM around dwarf galaxies. And I'll just say that my next project is really focusing on comparing to O6 detections at a slightly higher redshift. So very excited about that. And in the last minute or so, I do also want to point out that in addition to comprising different masses, the cool and warm phase actually exhibit a very similar metal retention rate. And so what I have here is compared to the stellar mass or median stellar masses for each of these points, the fraction of metals retained in the cool and warm phase. And so the warm phase is our orange points, and then the cool phase is our blue. And so what we can see is that across stellar masses, these phases are generally retaining about 10% of the metals ever produced. And so I think this also, again, motivates why we should be looking into, or why we care about both of these phases. And finally, this is my summary slide. I also want to, before I say thank you to the organizers for letting me speak and for all of your time. Thank you very much.
So I'll just take Chair's prerogative to ask a question first. So what colour is your favourite M&M?
Oh, I'd say blue.
I'll start this side.
Thank you. I wonder, you mentioned about the blast wave supernova feedback and the super bubble supernova feedback. Could you please shed a light on it? What's the meaning, the difference between these two?
Yeah, so blast wave, so the biggest difference between them is how they choose to model the evolution of the supernova. And so both will impart about 10 to the 51 ergs of energy into the surrounding, and then that will cause some heating of the gas. And so in the blast wave model, we have the initial heating, and then there's a momentum conserving phase, or the set-off-Taylor phase, where cooling is turned off, and this will expand. And on some time scale, about 1 million years, cooling will turn back on, and then that will convert into the snow cloud phase. Superbubble is slightly different, where instead of just imparting this energy into each particle, it allows for particles to be two-phase. And so if there's some energy imparted to this particle that doesn't fully heat it, it can split into two phases, and then we have some subgrid models for modeling the interaction between those two phases to eventually bring them back to one. So that answers that question.
Have you looked at the kinematics of the
No.
different phases?
I have not. I think it's going to be in my next paper in the 06. I've kind of crammed a lot to this morning.
So I was curious about your last figure where you showed that retention fraction is very small. If you look at observations, like I don't think going down to 6.5 but 10 per 8-ish, you'd find that majority of the warm and cold gas is consistent with being bound.
Okay.
Does it mean that your feedback prescription is a bit too efficient or too strong?
I'm not sure. I guess, so you were asking, would you mind rephrasing that question? Or like repeating it, sorry?
So if you look at what fraction of gas is consistent with being bound to the dark matter halo,
Yeah.
up to 10 rates solar mass at least, I can comment on that. Majority of the gas is consistent with being bound rather than being escaping, which, if I understand correctly, is the opposite of what you're showing. Does that mean your feedback prescription is too slow? Which in turn will have effect on your radial profile.
I'm not sure. I think I'll have to look into it a little bit more. There's another grad student who's looking at specifically inflows and outflows and mass loadings, and I think that could be really useful in kind of answering that question a little bit more. But I'd love to chat about that more.
If Priscilla wants to come up. There was a question at the back. Did you have a question at the back? So that, going back to this question, so this is within the virial radius that you're measuring this thing.
Yeah.
Because there was the previous talk about going out all the way out to R25, 25 times that sort of thing.
Yeah.
But, yeah.
So I think it would be really interesting to kind of push us further out into seeing where exactly are those metals.
Yeah.
But I haven't done that quite yet. And I guess if you remember back to Nishant's talk, they showed a column density, or like a map of metals in Mina's paper. And that is kind of showing a metal-enriched region on the scale of like 2 megaparsec-ish. And so we see a similar distribution as well. And so that does show us that there's a lot of material in like metals, just for us out to those megaparsec scales.